Now that we've covered the four foundational patterns, let me give you some practical guidance on designing your own DSL. The most important thing is to start with the user experience. And I want to emphasize this point because it's where most people go wrong. Before writing any implementation code, write examples of how you want your DSL to be used. Focus on expressing domain concepts as naturally as possible. Now, here's an example of what I mean. Look at how this reads. We are creating a validator that requires an email, requires that the email contains an @ symbol, wants if there's no phone number, and conditionally requires a parent email for minors. This reads almost like natural language, but it's still valid Java code. Notice how this reads like a description of the validation rules, not like implementation details. The person using the DSL doesn't need to know about loops, conditionals, or data structures. They just express the business rules directly. This example driven approach helps you discover the right abstractions before you get caught up in implementation complexity. It's best to write several examples of how you want your DSL to be used. Then work backwards to figure out what classes and methods you need to make those examples work. The other thing is build incrementally. Start with basic combinators that can be composed. Then add wrapper capabilities for cross cutting concerns, create fluent interfaces for better usability, and finally move to interpretation if you need ultimate flexibility. For our validation DSL, you might start with, you know, the combinator foundations. A validation rule takes an object and returns a validation result. The AND method is our combinator. It creates a new rule that applies the first rule, and if that passes, it applies the second one. Then you can add a fluent builder pattern for the domain abstraction layer. The require method creates a validation rule from a predicate and an error message, adds it to the list, and returns this for chaining. The build method combines all the rules into a single validator. Also, it's important to maintain type safety. Use the type system to prevent invalid combinations and make illegal states unrepresentable. Here, we've used a separate builder type for conditional validation. This ensures that conditionals requirements can only be added in the right context, and that you have to explicitly end the conditional block to return to the main builder. The type system prevents you from creating uh, invalid validator configurations. Now that you understand how to build DSLs, let me warn you about some common pitfalls that can derail your efforts. These are the mistakes I've seen repeatedly and I've made repeatedly as well. And avoiding them will save you significant time and frustration. The biggest temptation is over engineering from the start. Don't try to build a comprehensive DSL that handles every possible use case from day one. This usually results in complex, hard to use interfaces that nobody wants to adopt. I've seen teams spend months building elaborate DSL frameworks before writing a single line of business logic, only to discover that their abstractions don't match real world usage patterns. Instead, start with the simplest possible DSL that solves real problems. Build the minimal set of combinators needed for your immediate use case, then expand based on actual needs rather than hypothetical requirements. If you need to process CSV files with three types of operations, build a DSL that handles those three operations well, rather than trying to anticipate every possible data processing scenario. Watch out for leaky abstractions. DSL users don't need to understand implementation details to use the DSL effectively. If your user needs to know about your internal data structures, your exception handling strategies, or the difference between different internal step types, your abstraction is leaking. For example, if your DSL throws a null pointer exception with a stack trace that shows internal class names, that's leaky abstraction. Instead, catch internal exceptions and rethrow them as domain specific exceptions with meaningful error messages. Keep your interfaces clean and your error messages meaningful. Users should be able to accomplish their goals using only the vocabulary your DSL provides. Be aware of performance overheads. Multiple abstraction layers can impact performance, especially in tight loops or high throughput scenarios. Each wrapper adds a method call, each combinator adds object creation, and fluent interfaces can create many intermediate objects. This doesn't mean you should avoid DSLs, but you should profile and optimize critical paths. Consider providing both high level DSL interfaces for clarity and lower level interfaces for performance critical codes. The two can coexist and even share implementation components. You might have a fluent DSL for configuration and setup, but provide a more direct API for the hot paths in your inner loops. And finally, debugging complexity. Deep abstraction layers can make debugging more difficult because the stack trace does, doesn't directly correspond to the user's mental model of what's happening. When something changes in a deeply nested combination of wrappers and combinators, it can be hard to trace back to the original problem. It's imperative to provide good error messages that relate to DSL concepts rather than implementation details. Consider adding tracing capabilities that can show the logical flow of execution in DSL terms. For example, instead of showing a stack trace through internal wrapper classes, show a trace like pipeline failed at step 3, which might be an email filter, because of an invalid email format at record 42. Let me wrap up by talking about the broader impact of DSLs on your development approach. When you start building software with internal DSLs, you're not just changing your coding style, you're changing your approach to system architecture. DSLs naturally lead to more modular, composable systems that can gracefully evolve over time. Internal DSLs represent a fundamental shift from writing code that does one thing to building languages that describe something. Combinators give you the mathematical foundations for unlimited composition through uniform interfaces and referential transparency. Wrappers allow you to add cross cutting concerns without polluting business logic, making your code more modular and reusable. Domain abstraction creates user friendly interfaces that speak your problem's domain language rather than your software accessible to making your software accessible to domain experts. An interpretation separates definition from execution, enabling multiple ways of handling the same logical descriptions. When you master these four patterns, you stop writing procedural codes that tells computers what to do step by step. Instead, you build vocabularies that can express complex behaviors through simple combinations. Your software becomes more reusable because components are designed for composition from the ground up. It becomes more testable because you can test individual components in isolation and test combinations independently. And it becomes more adaptable to changing requirements because you can create new behaviors by recombining existing pieces rather than modifying existing code. Now, the goal isn't to build DSLs for their own sake, but to create software that bends with your problems instead of against them. When you find yourself copying and modifying similar code patterns, when requirements change, require widespread modifications, or when domain experts struggle to understand your implementations, these are signals that a DSL approach might transform your development experience. Start small, focus on user experience, and build incrementally. The patterns will guide you towards software that's not just functional, but genuinely flexible. Thank you for joining me in exploring internal DSLs, and I hope these concepts help you build better, more maintainable software.